All right, so this is 6.6. This is another section that virtually every problem is I just cut and pasted from my intermediate algebra class. So if you were good in intermediate algebra and you haven't forgot a lot, this might be a really friendly section. A lot of the problems in this section can be done multiple ways. I'll probably do most of them just one way. And if you were doing the homework without me and you wound up getting the right answer and you used a different strategy, then likely you did the correct algebra. Each of the problems between 1 and 12 can be solved with and without logarithms. And even with logarithms, they can be solved two ways. So there's maybe at least 3 ways to solve these problems between 1 and 12. And most of the problems in this section will have multiple ways they can be solved. And it's up to you, if you don't like the way that I solved it and you came up with another way, to make sure that it's a correct way. You might want to visit me if you are trying to do something different than I do in the video and you want to know whether it's correct or not in terms of, well, whether it will work every time. A nice thing about this section is every problem has an equal sign, and every problem, the answer is going to be x equal to some number. Because we're getting numerical values and numerical answers, we can check. So I have my calculator out. I'm going to check every single answer to make sure I haven't made a mistake. The last couple problems in this section are set up so if you do perfect algebra, the algebra will generate every solution, but it'll also generate solutions that don't check. So if you aren't in the habit of checking the last 2 even problems in this section, that they need to be checked. Specifically, problems 48 and 50, what they have in common is there's 2 logarithms separated by a plus sign equal to some number. 48 and 50 are kind of structurally the same. Those 2 problems, if you don't check and you write down the 2 answers that your algebra produces, only one of the answers will check and you'll lose some points for writing down an answer that's not correct. Up until that point, if you don't check, there's not a danger of writing down a solution that you did correct algebra that doesn't work. For each of the problems between 1 and 12, they're problems like we've seen a couple times already, and if it's practical to write both sides of the equation with the same base, then I can solve the problem by dropping the bases and equating the exponents. Because it's easy to write 27 as 3 to some power, the easiest way to solve this problem is to do that. Take the 27, find the prime factorization. Because 27 is equal to 3 times 3 times 3 when I do a prime factor tree, I can rewrite 27 as 3 cubed, and anytime I can set the problem up so I have each side of the equation having the same base, I can drop the bases and equate the exponents. And because the exponent is just a plain x, doing that's going to give me my answer. The answer to problem 2 is going to be x equal to 3. I should always check because it takes 20 seconds to check, and that makes me know whether I've made a mistake or not. The original problem was 3 to the x equals 27. I think 3 cubed, or x equals 3, is the right answer. So that means if I go to my calculator and I put 3 in for x, the left-hand side I get 3 cubed. It should be the case when I do that 3 cubed that I get 27. I don't know if you can read sideways, but that gives me 27 equals to 27, so that answer is correct. Just for whatever reason, if I try to put it like that, you can't see it so well. So 3 is the answer. This is the checking. The checking is optional. There are other ways to get that answer, but probably not any quicker way to get that answer. 4 is similar. If I can write both sides as 3 to some power, I'm way ahead of the game. So I'm going to try to do that with 81. I'm going to make a prime factor tree for 81. 81 is 9 times 9. Each of the 9s is 3 times 3. Because it's not terribly hard to write 81 as 3 to some power, the easiest way to solve this problem is to rewrite the 81 So in this case, I'm going to rewrite the 81 as 3 to the 4th power and drop the bases and equate the exponents. If I couldn't write 81 as 3 to some power, then I'd have to use logarithms to solve this. But since I was able to write 81 as 3 to some power, I'm going to drop the bases, equate the exponents, solve. Whoops. I'm going to get 2 for an answer because we have x plus 2 equals to 4. I minus 2 from both sides, and that's going to give me the answer of x equal to 2. Again, I'm silly if I don't check because I can take 25 seconds to check. The original problem was 3 to the x plus 2 equals to 81. For my answer to be correct, it has to be the case that 3 to the 2 plus 2 power equals 81. So I'll just do that. I'll go 3 up arrow parentheses 2 plus 2. So there's 3 to the 2 plus 2 power, or not. And then I hit enter. It gives me 81, and because 81 equals to 81, because when I hit enter, the left and the right side are the same number, my answer is correct. And so I'm perfectly done, and I know that's the right answer, so I don't have to worry about having a mistake there. 6, I suspect that it would be hard for most of you to write 27 to the 1/3 power. I'm going to wind up doing this 2 ways. The way that is the clever way to do it, and then the logarithmic way. And there's probably 2 logarithmic ways, but I'll do 1 logarithmic way. So to write both sides as to write both sides as 1/3 to some power is tough. 27, if I did a prime factor tree for 27, 27 is 9 times 3, 9 is 3 times 3, so 27 is 3 times 3 times 3. It's not terribly hard to get the problem written like that. Unfortunately, that's not enough because both sides don't have the same base. So if I wanted to solve this by making both sides have the same base, I either make both sides have the base of 1/3 or both sides have the base of 3. It doesn't matter which. Turns out that it's not that hard to work on the left-hand side. If you know that 1/3 is 3 to the negative 1 power, then you could do good things. So that's what I'm going to do here. I'm going to rewrite the 1/3 as 3 to the negative 1 power and make that equal to the x equal to 3/3. And now I have 1 base, 2 exponents. I multiply the exponents. This is going to give me 3 to the negative x or negative 1x equals 3 cubed. And now I have the bases the same. I drop the bases, equate the exponents, divide both sides by a negative 1. I claim that the answer is x equal to negative 3. I'll check this. For checking, it needs to be the case that the original problem, 1/3 to the x equals 27, becomes a true statement when I make it 1/3 to the negative 3. So if I do 1/3 to the negative 3 on my calculator, it better give me 27. So I'll try that. I'm going to go parentheses 1 divided by 3, parentheses, up arrow, negative 3. When I hit enter, it best say 27. It does, so my answer is right. So if you were clever enough to think you could do that by yourself on a test, that's absolutely great. That'd be a perfect place to be. If you couldn't do that because it's a little bit beyond you, all of the problems between 1 and 12 can be solved with logarithms. There's 2 ways to solve them with logarithms. I'm just going to pick one of them, and it's the way that's going to work for all the problems coming up. So I'm going to redo live number 6. I'm going to do it with logarithms. I'll get the same answer. So problem 6, again, says 1/3 to the x equals 27. And a way to solve this problem with logarithms, specifically, I can take the logarithm of both sides. I can go the logarithm of 1/3 to the x equals the logarithm of 27. You can take that logarithm any base. I just did it base 10 because my calculator works in base 10. So if you couldn't do what I did for number 6, This strategy turns out, once you do it enough times, to be the mindless way to do it. It's the easier way to do it. You don't have to be clever. Each of the problems between 1 and 12 I can solve exactly like this. Take the logarithm of both sides. Now I'm going to use the rule that says exponents can be multiplied. So this is going to be x times the log of 1/3 equals the log of 27. And now I'm going to divide both sides by the log of 1/3. On the left side, the logs cancel. I'm left with an x. On the right side, I'm going to break my calculator out. And on my calculator, I'm going to enter essentially that. I'm going to go the log of 27 divided by the log of 1 divided by 3. So I'm entering basically exactly what I see, kind of the best I can on my calculator, and it gives me the -3. That is the answer. So both strategies work. For each of the problems between 1 and 12, if you find it difficult to write each side with the same base, then the taking the logarithm of both sides strategy will work perfect for solving the problem. It's not the only way to solve the problem using logarithms, but it's a way that works just fine. Gives me the same answer. So I got -3 and -3. 6 only has one answer. The answer is -3. It's just a matter of how you go about getting it. It will check regardless of how you get it, whether you use logarithms or you don't use logarithms, it'll work just fine. So 8 is not hard to do with the bases because 243 is a power of 3. If I do a prime factor tree for 243, 243 is 3 times 81, because if you go 243 divided by 3, you'll get 81. 81 is 9 times 9. 9s are 3 times 3. So this is going to be 3 times 3 times 3 times 3 times 3, or 3 to the 5th power. So I can easily, without really being that clever, write both sides as 3 to some power. If that's the case, if it's easy to write both sides with the same base, then you do that. You solve the problem by dropping the bases and equating the exponents. Probably the easiest thing to do here. I'm going to add x and -5 from both sides, because it's going to make my x positive, and I like positive x's better than negative x's. If I -5 from this side, I get a 0. The x's also cancel. On this side, if I -5, I get a 0, and I still have the plus x. I claim that the answer is x equal to 0. And again, I'm going to check that because it's not supposed to be that hard for any of these to check. Whether I did them with logarithms or without logarithms, the checking is supposed to be easy because my calculator makes checking easy. So it should be the case that 3 to the 5 minus 0 power is 243. So I go 3 up arrow parentheses 5 minus 0 power, and when I hit enter, if it gives me 243 like it does, my answer is correct. If I hit enter and it didn't give me 243, then I'd have a mistake. All of the problems have solutions, so that you should always be able to get a number that checks. Could do this with logarithms, but logarithms are, we'd say it's like killing an ant with a sledgehammer, I guess, in a higher math course to use logarithms to do this. 10 I'll do both ways. I'll do it with logarithms and without. I can write both sides as 3 to some power. The right side, 3 is really 3 to the first power. The 27 on the left side, 27, the prime factoring is 3 times 3 times 3. So 27 can be written as 3 cubed. Because 27 already has an exponent, when I rewrite the 27 as 3 cubed, I'll make the 3 cubed in a parenthesis so those two exponents aren't touching. Now I'm going to multiply those exponents, because if I have one base and two exponents, you can multiply the exponents. This is going to give me 3 to the 3x equals 3 to the first. Bases are the same now. I can solve the problem by dropping the bases and equating the exponents. divide both sides, and I get my answer of x equal to 1/3. Again, super easy to check. It should be the case that if I go to the original problem, which was 27 to the x equals to 3, if I go 27 to the 1/3 power, I should get 3. Easy enough to check. I go 27 up arrow parentheses 1 divided by 3 and hit enter. And when I hit enter, it tells me that I haven't made a mistake because I got 3 equal to 3. If you didn't like that, you could do you can do number 10 with logarithms. And so let me do this with logarithms just in case you didn't, that wasn't something you want to try. All of the problems between 1 and 12 can be done by taking the logarithm of both sides. So let me do that. So this is an alternate way to do it. This is a logarithm approach. So you can go the logarithm of 27 to the x equals the logarithm of 3. Now I'm going to bring the x out front and make x times the log of 27 equals the log of 3. Now I'm going to divide both sides by the log of 27. So this logarithm strategy, once you start doing it, it's the same for every problem, so in some sense it's nice. On the left-hand side, the logs cancel, I'm left with the x. On the right-hand side, I'm going to do my calculator. I'm going to get a decimal answer, I'm going to make it into a fraction. So I'm going to go log of 3 divided by log of 27, hit enter. Decimals I don't want. To make a decimal into a fraction, I hit the math key and enter twice, and I get 1/3 for the answer. So taking the logarithm of both sides will work to solve any problem that has an equal sign and an exponent. Making both sides written with the same base, that's not always so easy to do. So sometimes we resort to logarithms. And sometimes it's impossible to make both sides have the same base. So 12 is kind of the same as the last problem. 7, I can think of as 7 to the first power. 49, because 49 is 7 times 7, I can rewrite the 49 as 7 squared. So if I'm doing it without logarithms, this is the strategy that I do. I write the 49 as 7 squared. I multiply my exponents. I get 7 to the 2x equals 7 to the first. Bases are the same. I drop the exponents. I get 2x equals to 1. Divide by 2, divide by 2. I get the answer that I'm going to check, because it's easy to check, of x equal to 1/2. To check this, I can go 49 to the x equals 7. It should be the case that 49 to the 1/2 power equals 7. So I pull my calculator out. I go 49 up arrow parentheses 1 divided by 2. And I get 7 equal to 7. So my answer is correct. Again, if that was above you, then you could have done this. You could have done the log of 49 to the x equals to the log of 7. Move the x out front and go x times the log of 49 equals the log of 7. Divide both sides by the log of 49. When you do that, you're going to get x equals on the left side. On the right side, I use my calculator to do log of 7 divided by log of 49. I get a decimal answer. I hit math and enter twice. Makes that answer into a fraction. So both strategies are going to give you the same answer. Anytime there's an x in an exponent, logarithms will be an effective strategy to solve the problem. Using this strategy will only work for a finite number of problems. If it's reasonably easy to write both sides with the same base, this strategy is probably preferred. But often it's impossible or too hard to write both sides with the same base, and this strategy you resort to. For number 14, it's going to be impossible to write 10, because if I did a prime factoring for 10, I can't write 10 as 2 to some power. So since I can't write 10 as 2 to some power. I can't use the non-logarithm approach. So the non-logarithm approach implies you can write both sides with the same base, but I can't here. The only way to solve this is going to be introducing logarithms. So I'm going to take the logarithm of both sides. I'm going to make the exponent x a coefficient. I'm going to divide both sides by the log of 2. On the left side, the logs cancel, and I have my x. On the right side, I'm going to round something to 2 decimals. You can tell that your answer, you couldn't have got your answer without logarithms when you get an answer that has a really nasty decimal expansion. So to do this, I'm going to go log of 10 divided by log of 2. I get 3.3219. Rounding to 2 decimals, I'm going to write 3.32. And so for my answer, it's a rounded answer, so I should probably put a squiggly, meaning it's not an exact answer, is 3.32. I'm going to check, but my checking is not going to come out perfectly because my answer is rounded. So the original problem said 2 to the x equals to 10. I'm going to write 2 to the 3.32 power and show you that that equals to 10, or something close to 10. So if I go 2 up arrow 3.32, I get 9.9866 equals to 10. Even though 9.9866 doesn't equal to 10, it's close enough to 10. Had I taken and did 2 up arrow 3.321928095, which is the unrounded answer on my calculator, if I did that, then I would have actually got 10 equal to 10. So when I'm checking a rounded answer, I don't expect a perfect check. I expect a close check because 9.9866 is close to 10. I think I'm probably right. So each of the problems between 13 and 24, I'm going to take the logarithm of both sides. It's going to be impossible to write both sides with the same base. On 16, because one of the bases is e, it will be nice if I take the ln of both sides. Usually I just take the log of both sides, but when the base on with the logarithm is e, you should take the ln of both sides. This is because the ln of e is equal to 1. So if I took the ln of both sides as opposed to the log of both sides, I'd get this. Now I'll divide both sides by the ln of e. Break out my calculator. It turns out that this piece is 1. I don't really need to do this piece, but let me do this on my calculator anyways. So I'm going to go the ln of 1.15 divided by the ln, and then I need to find the e. My eyes are, it's really pushing my eyes right now to find that e. The e is on the divide key. So I'm going to go second divide to get the ln of e. So I'm able to get the ln of 1.15 divided by the ln of e written, because for the ln of e, I use the second and up arrow. And this gives me my answer of 0.1397. And for 0.1397, the 9 in the third position is going to round it up to 0.14. So for my answer, I'm going to write 0.14. This piece right here, this ln of e, I could have did this. Instead of doing what I did, when I had x times the ln of e equals the ln of 1.15, the ln of e, let me show you on my calculator, second ln of e, ln second e, the ln second up arrow, really, second divide, just with the glare I can't see. The ln of e is equal to 1. So this problem, x times the ln of e, is really x times 1 equals the ln of 1.15. And this gives me x equals the ln of 1.15. If on my calculator I just did the ln of 1.15, without the divide part, I still get this same 0.1397619. You'd get the same answer because the ln of e is equal to 1. I didn't really need to divide. I could have just said this is x times 1, which is x, and still got the same answer. Let me check this. Should be the case that e to the 0.14 power should be about 1.15. Taking the answer that I think is correct, putting it in for e, should give me a close checking. So I'm going to go second in ln to get e to the power. I'm going to go 0.14. And when I hit enter, I hope to get something close to 1.15. And I get 1.15027. That's close enough for me to believe I have the right answer. 18 and 20 are a little bit different. You'll see the parentheses, the 4 next to the 3 in parentheses, the 14 next to the 3x. Both of those numbers, the 14 in problem 20 and the 4 in problem 18, they're on the side with the exponent, but the exponent doesn't apply to them. When I do 18 and 20, the first thing I need to do is make the piece with the exponent get isolated, and I'm going to divide both sides by 4. When I divide for 18, and in 20 I'm going to divide by whatever that number is to divide by. So in 18 I need to rewrite the problem so that only on the left-hand side is the 3 that the exponent applies to. Now I'm going to take the logarithm of both sides, do the logarithm of 3 to the x equals the logarithm of 6. Bring the x out front. I go x times the logarithm of 3 equals the logarithm of 6. Divide both sides by the logarithm of 3. The right side, I need my calculator. The left side, I get my x. So now I'm going to do log of 6 divided by log of 3. And when I do log of 6 divided by log of 3 and round it 2 decimals, I get 1.630. I'm just going to write 1.63 for my answer. Now I'm going to check it. Throw the checking right up here. For checking, I should take this answer, go 4 parentheses, 3 to the 1.63 power, and I should get something that's close to 24, but not exactly 24 because my answer is rounded. So when I go 4 parentheses, 3 up arrow 1.63, I hope to get something close to 24, and when I do that I get 23.975 is about 24. That's close enough for me because I have a rounded answer. 23.975 rounds up to 24, so I believe my answer is correct. So 18 had a little twist. It had something on the left side that didn't apply to the exponent. It was more clear in 18 that the x didn't apply to the 4. It might not be as clear in problem 20 that the 3x doesn't apply to the 14, but it doesn't. For the 3x to apply to the 14 would need to be in a parentheses. So just like on 18 I divided to get started to get the piece with the exponent isolated, I'm going to do that here. This is going to give me e to the 3x equals 3. And I'm going to take the ln of both sides because the ln of e is 1. I'm going to bring the 3x up front. I get 3x times the ln of e equals the ln of 3. Because the ln of e is 1, this is really 3x times 1 equals the ln of 3. It happens all the time in brief calculus that you use the ln of e as 1, so it's something just good to get in your head. So this piece, that ln of e, second ln, second divide, the ln second divide, the ln of e is equal to 1, so I can replace the ln of e anytime I see it with a 1. So this problem comes 3x equals the natural log of 3. I'm going to divide both sides by 3. I get x equals the ln of 3 over 3. That's calculator. So I'm going to go ln of 3 parentheses divided by 3. Enter it more or less how it's written. And the ln of 3 divided by 3 is 0.366, and instead of 0.366, I'm asked for 2 decimals, I'm going to round that to 0.37. So I'm going to say x equals 0.37 for my answer. and then I'm going to check. The checking is going to be going up into the original problem and going 14 times e to the 3 times 0.37 and see if that comes out to be close to 42. It doesn't have to be perfectly 42. 41.9, 42.1 would be close enough because this is a rounded answer. My answer probably should also have that squiggly because it's rounded. So let me try to check. I'm going to go 14 and then second ln to get the e. And then the exponent is 3 times 0.37. So that is more or less what I'm trying to make equal to 42. And when I hit, whoa, really? Oh, I didn't do 37 right. So look, I did negative 37 and not 0.37. Look how bad it didn't. It was bizarre. So I should have went 14 second ln 3 times 0.37. It says glare on the calculator. It makes it hard to see the buttons properly. And I get this. I get 42.48 is approximately 42. That's pretty far away. Let me check this 0.366. If I did 14 second ln 3 times 0.366, if I round it to 3 decimals, it's better. 41.97 equals, that's much closer to 42. So my rounding was pretty severe because I rounded the 6 up to a 7 and the checking came pretty far off. But when I did this, 14e to the 3 times 0.366, I got 41.97 is a 42. So I think my answer is correct. It's just the checking was almost off a half because my rounding caused that to happen. So rounding can definitely wreak havoc in your checking. The more decimals you carry, the better your checking is going to happen. But it'll never be exact. Problems are a mess. 22 is not a fun problem because both of the sides have an exponent. These are going to really test your patience a little bit. Took the log of both sides just like I did the last few problems. I'm going to make the coefficient into an exponent, or the exponent into a coefficient. And on the right-hand side, I need to use a parentheses because the exponent has a subtraction in it. So I get x times the log of 2 equals x minus 1 times the log of 3. I'm going to do the multiplication on the right-hand side and get x times the log of 2 equals x times the log of 3 minus 1 times the log of 3. Need to get my x's on one side, so I'm going to minus x the log of 3 from both sides. When I do that, I get x log of 2 minus x log of 3 equals minus 1 or minus log of 3. I don't need to write the 1 in front of the log, but I could. Now on the left-hand side, I'm going to factor out a common factor of an x. When I factor out an x, I'm left with the log of 2 minus the log of 3 equals the minus log of 3. Now I'm going to divide both sides by the log of 2 minus the log of 3. On the left-hand side, I get my x. On my right-hand side, that is the answer to this problem, minus log of 3 over log of 2 minus log of 3, which I'm going to get a decimal equivalent for. So I'm going to go, hopefully you can see this well, minus log of 3, parentheses, divided by, and put this in a parentheses, so parentheses, log of 2, parentheses, minus log of 3, parentheses, parentheses. So I entered log of 3 divided by, and then the whole denominator I put in a parentheses. So I had that parentheses, and then I had the 2 and the 3 in the parentheses. So I have the log of 3 in parentheses, minus log of 3 in parentheses for the numerator. In the denominator, I have a big parentheses capturing the whole denominator, little parentheses around the 2 and the 3. And when I hit enter, I get and I'm going to round that to 2.71. It's 2.709. I'm going to say that's my answer, and now I'm going to check it. For checking, I go to the original problem. It has to be the case that 2 to the 2.71 power is about 3 to the 2.71 power minus 1. So there's two x's. I have to put the x's in each. The left-hand side, if I go 2 up arrow 2.71, I get 6.54. Hopefully the right side comes out to that as well. On the right side, if I go 3 up arrow parentheses 2.71 minus 1, the right side comes out to be rounded 6.54. They're not exact, 6.543, 6.544, but they're close enough, so I believe my 2.71 answer is perfect. This is the technical correct answer. This is the unrounded perfect answer written in logarithmic form. I'm content with the decimal answer, but in a calculus class, you might get a teacher that wants an answer that looks like this. So if I didn't enter this on my calculator, it wouldn't be wrong to say x equals negative log of 3 minus over log of 2 minus log of 3. That's actually the exact answer to problem 22. Unsimplified, undecimalized. But this is content for me. Same sort of deal. 24 is also a messy problem. I'm going to take the logarithm of both sides. I'm going to go the logarithm of 2 to the x equals the logarithm of 6 to the x minus 3. This gives me x times the log of 2 equals x minus 3 times the log of 6. Distribute on the right-hand side. I get x times the log of 2 equals x times the log of 6 minus 3 times the log of 6. Now I'm going to minus x log of 6 from both sides. When I do that, I get x log of 2 minus x log of 6 equals minus 3 log of 6. Plot my common factor of x on the left-hand side. This gives me x log of 2 minus log of 6 equals minus 3 log of 6. Divide both sides by log of 2 minus log of 6. This is technically the answer that I'm going to get a decimal equivalence for. The left-hand side, I cancel. I'm left with the x. On the right-hand side, I'm going to use my calculator to figure out a decimal approximation for that. Sorry about that phone going off. I never have my phone with me. And my sister never calls me, which is bizarre. It's got to be something moderately important. So let me do this. Minus 3 log of 6 divided by, and then bunch of parentheses down here. I'm going to do log of divided by big parentheses. Now a text message. Divided by log of 2 in a parentheses minus log of 6 in a parentheses and another parentheses. So that's a mess to do. So I have negative 3 log of 6 divided by, and then the denominator has 1, 2, 3, 4, 5, 6 parentheses, and I get 4.89 for a 2 decimal version of this. I'm going to check this. So I'm going to check this to see if 2 to the 4.89 power is about 6 to the 4.89 power minus 3. Pull out this calculator. Hopefully you can still see this. So I go 2 up arrow 4.89, and that gives me 29.65 rounded. And then I'll do this other side. 6 up arrow 4.89 minus 3. And that gives me syntax error. Go to that. I didn't need a parentheses. I needed the whole thing in a parentheses. I need 6 up arrow parentheses 4.89 minus 3. And I get 29.56. So that's not a beautiful checking. 29.65 doesn't equal 29.56, but because my answer is rounded, I don't expect an exact checking. I just expect a close checking, and because that's close, that makes me believe if I carried more decimals than just these 2 decimals, that I'd get a closer checking. And I believe my answer is right. And I don't, if I wanted to, I could go back and check a longer, more decimal version, a less simplified version of that answer and see how it works. So all the problems up through 25 don't have logarithms, and I introduced logarithms to solve them, or wrote both sides with the same base if that was easy for me to do. The rest of the problems all have logarithms, and to solve them, I need to get rid of the logarithms. So let me do these. Easy to check these as well. So for each of the problems between 25 and 51, I'm going to do something to get rid of the logarithm. And that's going to vary from problem to problem. But most of the problems, I'm going to get rid of the logarithm by writing something that's equal to the original problem without a logarithm. For problem 26, I'm going to scratch out the logarithm. I'm going to leave the base too low, and I'm going to switch the 3 and the x. So I'm writing something equivalent to the original problem that doesn't have a logarithm, which we've done already. Got rid of the logarithm. The base was 2. It stays the base. I switch the 3 and the x. 2 cubed I don't need my calculator for. 2 cubed I believe is 8. I believe 8 is the answer. If I want to check, it should be the case that the log base 2 of 8 equals to 3. I'll check this on my calculator by going log of 8 divided by log of 2. When I do log of 8 divided by log of 2, that gives me 3 equal to 3, so my answer is correct. For my answer to be correct, I need to be able to plug it back into the original problem, simplify, and have a true statement come out. 28, if I'm doing this, the shorthand notation of ln is not beneficial for doing algebra by hand. It's beneficial for my calculator, but not for hand arithmetic. So I changed ln to log base e because they're equal to each other. Now I'm going to write the problem without the logarithm. I write something, the logarithm goes away. The e that's the base stays the low. I switch the 0 and the x. So writing the problem ln of x equals 0 without a logarithm, you get e to the 0 equal to x. Anything to the 0 power is 1, so that gives me x equal to 1. I believe that's the answer. This is going to be easy to check because calculators do well with ln's. So when I go to check, I put the 1 for x into the ln, and it should be the case that the ln of 1 is equal to 0. I put parentheses in sometimes I don't. It's not a deal breaker if you do or don't put them in for me. So if I do the ln of 1 on my calculator, this gives me that I didn't make a mistake, that 0 equals to 0. Those problems were friendly. The algebra for the next few problems might be a little bit tricky. And there's these parenthetical comments that say x is greater than 0. This just means if I do algebra and my algebra produces negative and positive solutions, that I only want to accept positive solutions. So this says the only solutions that we'll consider here are positive. Bases for logarithms are usually restricted to positive values. And so if I happen to get a negative solution, I'm just going to ignore it and only include positive solutions. So 30, I'm going to start off the same way. I'm going to write the problem without the logarithm. The x was low. It's going to stay low in the non-logarithmic form. I'm going to switch the 3 and the 27. I know the answer to that without doing algebra, but the algebra to solve x cubed equal to 27 would be to take the cube root of both sides. I do the cube root of x cubed equals the cube root of 27. The cube root of x cubed, cube rooting cancels out a cube and gives me an x. The cube root of 27, if I want to do that on my calculator, I hit my math button, go down to option 4 that says cube root, type 27, and the cube root of 27 is going to be 3. So this is going to give me 3 for an answer. I'm going to check this. So this is supposed to be my answer. If I want to check, it should be the case that if I go the log base 3 of 27, that it should equal 3. And I'll do this by going log of 27 divided by log of 3, and that gives me a true statement that 3 does equal to 3. So my checking checks. 32 has the same parenthetical comment. Again, it means I only can have positive solutions. It's not going to impact the algebra. Write this without the log. Take out the log. The x stays low. I switch the 5 and the 32. Gives me x to the 5th equals the 32. To solve this, I have to 5th root both sides. So again, some algebra that we might have not done this semester. You might not have seen that since intermediate algebra. So it's going to come back, and it's going to be in calculus. Algebra just comes back all the time, and you just eventually get good at figuring out what algebra is appropriate. On the left-hand side, 5th rooting cancels out the 5th power. 5th root of 32, I know what it is. Tricky to do on the calculator. To do the 5th root of 32 on this calculator, if you didn't know it in your head, you type the number 5, you hit the math key, you arrow down to option 5, which is a radical with an x, and hit enter. So I see 5x radical, then I type 32. That's the 5th root of 32 on this calculator, which is 2. So again, I did this. I hit 5, math, went down to option 5 with the radical with the x, then I type the number 32 and hit enter. Tells me the answer to this problem is 2. I can check that. For checking, I'll go the log base 2 of 32, see if that equals to 5. Pull out my calculator on the left-hand side, do log of 32 divided by log of 2, and that tells me that I haven't made a mistake, that 5 equals to 5. So the beginning problems with the logarithms all kind of start out the same way. The algebra might get a little bit tricky depending on how the problem's set up, but nevertheless, it's not going to be horrible, except the algebra part maybe. This problem, again, I'm going to write it without the logarithm. The x is going to stay low. I'm going to switch the 1/3 and the 4th. I know that 1/3 power and cube roots are the same. 1/2 power and square roots are the same. I'm going to rewrite this as the cube root of x equals to 4 because 1/3 power and cube roots are interchangeable. To get rid of a cubed root, I cube both sides. On the left side, cube rooting cancels out the cube root symbol, leaves me with the x. On the right side, 4 cubed is 4 times 4 times 4, which is 64. I should check this just to make sure. My checking should be the case that the log base 64 of 4 equals to 1/3. When I do this on my calculator, I'm going to get a decimal, and I'll math enter to make it into a fraction. So my checking, I'm going to go log of 4 divided by log of 64 equals, gives me a decimal, and then math enter, and this gives me 1/3 equals 1/3, and that's what I need to have for an answer to be correct. 36, same deal. I have one logarithm equal to a nice number. I'm going to write the problem without the logarithm. Delete the logarithm. The 3 stays low. I switch the 2 and the x minus 5. When the x minus 5 is written on the right-hand side, it doesn't need to be in a parentheses anymore. Solve this. 3 squared is 9. This gives me 9 equals x minus 5. Add 5 to both sides and get my answer of x equal to 14. Check my answer. Go to log base 3 of 14 minus 5 and see if that equals to 2. Do that on my calculator. Do the log of 14 minus 5 divided by the log of 3. When I do that log of 14 minus 5 divided by the log of 3, I get 2. And that means my answer is correct because the right side was 2. So when I plug 14 in for x, simplify the left-hand side, it simplifies to be the right-hand side, so my answer is okay. That space probably shouldn't be there in 38. That's the base is 3, the argument is 3x. I'm going to cross out the logarithm, write this as 3 to the 0 power equals 3x. 3x doesn't need to be in a parentheses when I clear it from the logarithm. Anything to the 0 power is 1. So I get 1 equal to 3x. Divide both sides by 3. We get 1/3 equals to x. when I go to check, should be the case that the log base 3 of 3 times 1/3 equals to 0. Easy enough to check. So I go log of 3 times 1 divided by 3 for that, and then divided by the log of 3 for the base. And then when I hit enter, hopefully I think a 0 there, and I do. So I get 0 equals to 0, so my answer checks just fine. So literally it takes 15 seconds to check. So on the test you should have 15 seconds to check any problem like this. The next few problems are all of a sudden different. The next few problems we will solve differently. How they're structurally different is they have one logarithm equal to another logarithm. The logarithms are the same base. For these problems, I can just drop the logarithms and equate the arguments. So I'm not going to do like I did for the last few logarithm problems. The last few logarithm problems only had one logarithm. Solving those is different than solving problems with two logarithms. And this style of two logarithm problems, where you have one logarithm or one natural log equal to another natural log, you solve the problem by dropping or setting the arguments equal to each other. And this is easy to solve. Now I minus x and add 10 to both sides. So structurally, you should notice the difference between this problem and the last few problems. Here on the left-hand side, -4 and 10 is +6. The x's cancel. On the right-hand side, 2x minus x is x. The 10's cancel. I claim this is the answer. For it to be correct, I should be able to plug 6 in. It should be the case that the ln of 6 minus 4 equals the ln of 2 times 6 minus 10. It has to check exactly because it's not a rounded answer. So let me do the ln of 6 minus 4. The ln of 6 minus 4 is 0.693147. You can see that. There's got to be a spot somewhere in there that you can see. But anyway, so left-hand side is 0.693. And when I do the right-hand side, do the ln of parentheses, the ln of 2 times 6 minus 10. It gives me also 0.693. So both of them give me exactly the same thing, the ln of 6 minus 4, just so you can see it. They're exactly the same. They check perfectly. So 6 is the correct answer. 42 is structurally the same, even though the logarithm is a different base. I have one logarithm equal to another logarithm, same base. Those style of problems you can solve by dropping the base and equating the arguments. For this problem, I'd solve it by minusing 3x from both sides. And when I do that, I get 6 equals to x for my answer again. Checking should be the case that the log base 4 of 3 times 6 plus 6 equals the log base 4 of 4 times 6. You can actually check this without your calculator because the left-hand side comes out to be the log base 4 of 18 plus 6. That's the log base 4 of 24. The right-hand side is the log base 4 of 4 times 6, which is also the log base 4 of 24. These have to be the same because the log base 4 of 24 equals the log base 4 of 24. So I could actually check that without my calculator if I care to. So those two problems had two logarithms, and I solved them specifically this way because the structure is they had one logarithm equal to another logarithm and the bases were the same. The next problems all have two logarithms, but I'm going to solve them differently. The structure part of these are different. The last two problems the logarithms were on opposite sides of the equal sign. Here are the logarithms on the same side of the equal sign. There's a minus between the logarithms. These problems are structurally different than the beginning problems that only had one logarithm. The last two problems that had two logarithms. These are their own unique little island. Eventually, this problem will solve more like the beginning logarithm problems than the last two. For this problem to get started, I'm going to use the minus to divide rule and rewrite the left-hand side so that it only has one logarithm. anytime I have two logarithms separated by a minus sign, I'm allowed to make, and they have the same base, I'm allowed to make the two logarithms into one logarithm if I divide the argument. The logarithm that's after the minus sign, its argument goes in the denominator. Now I'm going to write the problem without a logarithm, like the beginning logarithm problems. I'm going to get rid of the logarithm. The 3 is going to stay low. I'm going to switch the minus 1 and the fraction x over x plus 6. I know that 3 to the negative 1 power is 1 over 3 to the positive 1 power, so it's 1/3. So this gives me 1/3 equals x over x plus 6. And that's a classic cross-multiplying problem. I have one fraction equal to another, so I'm going to cross-multiply to solve this. Cross-multiply up, cross-multiply down. Cross-multiplying up, I get 3 times x. Cross-multiplying down, I get 1 times x plus 6. That gives me 3x equals x plus 6, because 1 times anything is itself, minus x from both sides, and get 2x equals 6, divide by 2, and get my answer of x equal to 3. Cumbersome to check, so I'm going to do this checking slow. In the original problem, if I did this, the log base 3 of 3 minus the log base 3 of 3 plus 6, that should be -1. Let me do each logarithm separately because it's too hard to do this whole left side in one big computation. So first logarithm, log base 3 of 3, I do log of 3 divided by log of 3. And that logarithm turns into a 1, so I'm going to change that to a 1, bring down the minus sign. And for this one, I'm going to do log of 9 divided by log of 3, because I could add 3 and 6 in my head. So I'm going to go log of 9 divided by log of 3. And when I do that logarithm, I get 2. So this logarithm, I did log of 3 divided by log of 3. That one, I did log of 9 divided by log of 3. The first one came out to 1. The second one came out to 2. That gives me 1 minus 2 equal to -1. I don't need my calculator to do that, but if I did, I can go 1 minus 2, and that gives me -1 equal to -1. So my answer 3 checks. And it's important to check. Pretty soon here, I'm going to get a problem and solve it, and one of my answers from perfect algebra won't check. 46, two logarithms separated by a minus, just like 44. Let's solve 44 just like 46. Specifically, when I have two logarithms separated by a minus on the same side of the equal sign, I'm going to use the minus to divide rule to make the two logarithms into one logarithm, taking the argument of the logarithm that's to the right of the minus and putting it in the denominator. Now I'm going to write this without the logarithm. I scratch out the logarithm. The 3 that was low is going to stay low. I'm going to switch the -2 and the x minus 5 over x plus 3. 3 to the -2 power is 1 over 3 squared, and 1 over 3 squared is 1/9. So I can write this as 1/9 equals to x minus 5 over x plus 3. I'm going to cross multiply again. Cross multiply down, cross multiply up. Cross multiplying up, I get 9 times x minus 5. Cross multiplying down, I get 1 times x plus 3. So this is going to give me 9x minus 45 equals x plus 3. I'm going to minus x and add 45 to both sides. On the left side, 9x minus 1x is 8x. The 45's cancel. On the right side, the x's cancel. 3 plus 45 is 48. And then I divide by 8. Divide by 8. I believe the answer is x equal to 6. Should certainly check that. So in the original problem, for my checking, I should go the logarithm base 3 of 6 minus 5 minus the logarithm base 3 of 6 plus 3, and that should equal -2. Let me do this logarithm first. So I'm going to do the logarithm of 1 divided by the logarithm of 3 because 6 minus 5 is 1. So log of 1 divided by log of 3 for that first logarithm. And when I do that, I get 0. So this is going to give me a 0 minus, and this one I'm going to do log of 9 divided by log of 3. So I go log of 9, because that's the 6 plus 3 divided by log of 3. When I do that, I get 2. So this gives me 0 minus 2 equals negative 2. Again, I don't need my calculator to do 0 minus 2, but I can use my calculator. And this gives me negative 2 equals negative 2, so my answer is correct. So every problem so far, I did algebra, checked my answers all checked, because I didn't really make a mistake. The next two problems, even when I do perfect algebra, I'm going to get an answer that doesn't check. 48 and 50 are both going to lead me to two answers, and one of the answers checks, one of the answers doesn't check. So if you didn't check anything up till now and you didn't make a math error, it wouldn't matter. 48 and 50, if you do your algebra and don't check and you write down the two answers that the algebra gives you, one of the answers isn't actually a solution. It's called an extraneous solution, meaning it's extra. It's an extra solution that the algebra generates that doesn't check. 48 and 50, what they have different than the last two problems is that instead of having a minus between the two logarithms, they have a plus between the two logarithms. I'm going to start off 48 and 50 by rewriting the left-hand side with one logarithm. And very specifically, I'm using the adding to multiply rule that we did in the last section that says if you have two logarithms with a plus sign between them and the logarithms have the same base, you can make the two logarithms into one logarithm if you multiply the arguments. And I'm going to do that multiplication. The multiplication is an x times an x and a 2 times an x. And so the left-hand side, I could write it as a logarithm base 2 of x squared plus 2x equal to 3. So I've cleaned up the left-hand side, made it down to one logarithm. Now I'm going to write the problem without the logarithm. I'm going to cross out the logarithm. The 2 is going to stay low. I'm going to switch the 3 and the x squared plus 2x. I have the first square that I have to deal with today. When I have a square, I usually solve by factoring. Before I can factor, I set the problem equal to 0. This side that's 2 cubed, I'm going to write as 8 because 2 cubed is 8. Now I'm going to minus 8 from both sides. And I get 0 equals x squared plus 2x minus 8. I'm going to factor that. That factors into x plus 4 times x minus 2. So I have the problem set equal to 0 and factored. I split each factor up and set each factor separately equal to 0. For the x minus plus 4, I minus 4 from both sides and get a potential solution of x equal to negative 4. For the x minus 2, I add 2 to both sides and get a potential solution of 2. Because the checking is rather involved here, I'm going to pull out another sheet of paper and do my checking. So there's two answers that I came up with. So one of the answers that I came up with is x equal to 2. I'm going to check that by going the log base 2 of 2 plus 2 plus the logarithm base 2 of 2 and see if that equals to 3. And this one I'm going to go log of 4 divided by log of 2. So I'll go log of 4 divided by log of 2, and that gives me a 2. So this piece comes out to be 2. And for this one, I'm going to go log of 2 divided by log of 2. And it gives me a 1. Since 2 plus 1 equals a 3, 2 is a solution. The next one I need to check is this negative 4. To check x equal negative 4, I'm going to go the logarithm base 2 of negative 4 plus 2 plus the logarithm base 2 of negative 4 equals to 3. This right here, I'm going to do logarithm of negative 2 divided by 2, and my calculator is going to give me an I, and that's going to make the solution not check. So when I do log of negative 2 divided by the log of 2, this is going to be, error, non-real answer. So I get an error on this calculator, plus, when I do that one, I'll do the same thing. If I do the log of -4 divided by the log of 2, your calculator might actually give you an I for this. It tells me non-real answer. It says something with an I plus something with an I equals 3. And whether your calculator gave you something with an I or it gave you an error message, when I get I's in my checking or I get errors in my checking, we say that number isn't a solution. It's an extraneous solution that doesn't check. So when I go to write my answer for problem 48, I have two choices. One choice is just to write the number that checks and not even comment about the -4. The other choice is you can write the answer that checks and also write the answer that doesn't check, but write something next to it that tells me that, yes, I know I got this via the algebra, but it's not really a solution because it doesn't check. So if I included both numbers in the solution next to the -4 that didn't check because error plus error doesn't equal 3, or something with an I plus something with an I doesn't equal 3, it would be best if I just didn't include that solution. But if I do include that solution, because it's not really a solution, I need to write something next to it to emphasize that it's not a solution. So this problem and its brother problem, problem 50, are the two problems in this section where you could do perfect algebra and get a solution that doesn't check. And you basically can tell in these logarithm problems, if you need factoring and you get two solutions, generally one of the solutions checks and the other doesn't. I'm going to do 50 just like 48, meaning I'm going to start off, because I have two logarithms separated by a plus sign, I'm going to make the two logarithms into one logarithm using the adding to multiply rule. I'm going to do the multiplication, multiply x times x and x times 12. This gives me the log base 4 of x squared plus 12x, x, 12x equal to 3. Now I'm going to get rid of the logarithm. The 4 is going to stay low. I'm going to switch the 3 and the x squared plus 12x. 4 cubed is 64. So I get 64 equals x squared plus 12x. I'm going to set the problem equal to 0 by going minus 64 and minus 64. This gives me 0 equals to x squared plus 12x minus 64. I think I can factor this. I need a plus and a minus, and I think it's going to be 16 times 4 for my last, because 16 times 4 is 64 and 16 minus 4 is 12. If I couldn't factor this, I could use the quadratic formula, but I can factor this. This factors into x plus 16 times x minus 4. You can FOIL it to check if you want to, but the inners are 16x, the outers are minus 4x. That's going to give me my 12x, and the last work as well. So I have it factored and set equal to 0. So I'm going to split the factors up, set each one equal to 0. The x plus 16, this is going to be the extraneous solution that doesn't check. I minus 16 from both sides and get minus 16. The x minus 4, I add 4 to both sides and get x equal to 4. That's the solution that's going to check. Again, these are a little bit trickier to check, so I'm going to give myself some room to check them on a separate sheet of paper. I'll do the one that doesn't check first, just to get it out of the way. So the original problem is this, and I want to check x equal negative 16. So I'm going to go the log base 4 of negative 16 plus the log base 4 of negative 16 plus 12, and see if that equals to 3. Immediately when I get an I or an error for either one of these, I'm going to stop and just say that's not a solution. So when I do this one and do log of negative 16 divided by log of 4, and my calculator tells me I get an error, this is going to be an error plus, and I don't care anything after this. Negative 16 is not going to be a solution. I get this hiccup when I try to check it, and as soon as I get the hiccup, I can stop. The next number that I came up with as a solution was x equal to 4. Hopefully that actually checks. So now I'm going to check x equal to 4, I'm going to go the log base 4 of 4 plus the log base 4 of 4 plus 12 and see if that equals to 3. For that one, I'm going to do log of 4 divided by log of 4. For this one, I'm going to do log of 16 divided by log of 4. So log of 4 divided by log of 4, I get 1. This one, log of 16 divided by log of 4, I get 2. And because 1 plus 2 equals to 3, 4 is a solution. And again, when I go to write my solution, I have flexibility. I could either just write x equal to 4 and stop for my answer and make no comment about the negative 16. Or I can write both the 4 and the negative 16, but next to the negative 16, if I'm writing it in my answer, because it's not really an answer, I need to say something that tells me, or the reader, that the algebra produced the solution, but it doesn't check. So writing is extraneous next to the negative 16 means that the algebra came up with it. It's not a solution, but I just want to show you that the algebra gave me that solution. So I'm showing you the algebra solutions, making the comment about the negative 16 that's appropriate. I know I went kind of fast. My hope was that most of this was review. If you took me for intermediate algebra, then you saw most of the problems. In intermediate algebra, I skip a few of these problems, but in college algebra, I don't feel the need to skip them. And if you didn't have me for intermediate algebra, or didn't have intermediate algebra recently, hopefully these are still things that felt kind of review. The next few sections, 6.7, 6.8, and 6.9 are all word problems. They're 3 word problem sections. They're not horrible, horrible word problem sections, so hopefully they don't bog you down. The nice thing about the word problem sections is there aren't near as many problems, and so the lectures go a little bit quicker than these just algebra sections. Okay, so if you're feeling like you're sinking, it's definitely the time to come visit me, stop by my office, and I can sit down with you and help you, recover if you're not feeling good about this stuff. Logarithms come up a ton in brief calculus and regular calculus, so it's really important to be really comfortable with logarithms. Otherwise, you're going to struggle a little bit more than you need to struggle in a calculus course if you need to take calculus.